Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore how modern AI frameworks and foundation models reshape the way we build, train, and apply large-scale neural systems across many domains.
It's a huge topic, really. It feels like we're living through this fundamental paradigm shift in artificial intelligence.
A paradigm shift? How so?
Well, historically, the way you'd build AI involved creating these very, very specialized tools for specialized tasks. So if you wanted to classify an image, you built an image classifier.
Right, one tool for one job, a text translator for translation, and so on.
Exactly. But what we're seeing now is completely different. We have these massive general-purpose models. You've heard the names GPT-3, BERT, DALL-E, and they're trained on these incredibly broad data sets.
Using a technique called self-supervision at a scale that was, frankly, unimaginable just a few years ago.
The scale is the absolute key here. I mean, the underlying ideas, things like deep learning and transfer learning, they've been around for a while. But when you push the architecture and the sheer volume of data past a certain point, something really surprising happens.
And that's where you start to see what researchers are calling emergent capabilities.
Precisely. That phrase is so fascinating because it gets at the heart of it. The model starts gaining abilities that nobody explicitly programmed into it.
They weren't even anticipated, right? It's like you pour enough water into a system and it suddenly figures out how to flow uphill.
That's a great way to put it. It's that same sense of unexpected function. You see things like in-context learning, where a model can perform a task it's never seen before, just from a few examples in the prompt. No retraining, no parameter updates.
And you need that immense scale just to unlock that kind of flexibility.
You do. And this whole revolution means that these foundation models, or FMs, they're the new starting point. They're sort of the core substrate for almost all specialized AI today, even though, they always need some refinement.
Okay, so let's unpack that transformation. Because it feels like it didn't start with the giant models themselves, but with the tools needed to build them, the infrastructure.
Right.
Let's start with the frameworks. Why are they so fundamental to this story?
Well, you simply couldn't have created foundation models without them. Before these tools, building a neural network meant coding all the complex math from scratch.
You mean handwriting the forward and back propagation, calculating all the gradients for every layer?
Every single time. It was incredibly tedious, really hard to optimize, and just full of potential errors.
So it was a completely bespoke process. Like if you were building a custom car, but you had to forge every piston and mill every gear by hand yourself.
That's the perfect analogy. And frameworks like TensorFlow, PyTorch, Caffe, they changed all of that. They provided these modular, pre-optimized components. They were like the prefabricated assembly line for AI.
And that move to modularity was what gave developers speed.
It was critical for velocity, yes. And the framework standardized a couple of major turning points. First, they automated what's called automatic differentiation. That's the math engine that lets the network calculate its errors and update itself efficiently.
So you didn't have to worry about the calculus anymore.
Exactly. And second, they came with built-in support for all these diverse pre-optimized architectures.
Which let developers focus on the model structure, not the low-level math. And we saw different frameworks get popular for different reasons, right?
Absolutely. TensorFlow, for example, got famous early on for its flexibility with these large computational graphs. It let you define the whole network structure first, then run it. That made it really robust for deploying on all sorts of platforms, from phones to huge GPU clusters.
And what about something like Caffe?
Caffe got a lot of traction because it was seen as the easiest to use at the start. It was really focused on rapid prototyping, especially for computer vision, even if it wasn't quite as flexible as the others.
So that focus on structure allowed engineers to think about the building blocks of intelligence itself, which brings us to a really core concept in neural nets. Nonlinearity.
It's truly foundational. If you have a deep neural network, say with dozens of layers, and you only use simple linear math, just adding and multiplying, all of those layers would just collapse.
They'd behave like one single simple layer.
Exactly. It wouldn't matter how deep it was, it could only model simple linear relationships. It would be pretty much useless for anything complex.
So the activation function is what breaks that simplicity.
Precisely. The activation function takes the data and transforms it in a non-linear way. It introduces the mathematical complexity the network needs to learn intricate features with every layer. It's what lets the model see the really complicated, non-linear patterns in the data.
Which is essential for recognizing a cat in a photo or understanding the nuance in a sentence.
And, the choice of that function was actually a huge roadblock for a long time.
How so?
Well, older functions like ton were really common, but they caused this massive problem called the vanishing gradient.
Ah, right, where the error signal gets weaker and weaker as it travels back through the network's layers.
It gets so close to zero that the early layers of the network just stop learning. The signal basically dies before it gets to the start.
And the weights don't get updated.
Correct. Which is why the introduction of the rectified linear unit, or ReLU, was such a game changer. It's a very simple function, conceptually.
It just outputs the input if it's positive and zero otherwise.
And that one simple change pretty much eliminated the vanishing gradient problem for positive values. Research showed that using ReLU led to much, much lower training times. Sometimes an order of magnitude faster than ton. It's what made training truly deep models practical for the first time.
Okay, so a better activation function solved the math problem. But scale requires more than just better math, doesn't it? It needs raw computational power.
Oh, absolutely. We can't talk about any of this without talking about hardware acceleration. The availability of specialized hardware-first GPUs, then later TPUs, was essential.
Because they're designed for the kind of parallel math that deep learning relies on.
Exactly. Every benchmark study across all the major frameworks showed the same thing, a massive speedup, often 10x to 100x, when you move from a CPU to a GPU.
So the frameworks provided the software architecture, the GPUs provided the computational muscle. You needed both.
You needed both working together. The frameworks let you define these enormous computational graphs and spread the work across hundreds of devices. The raw power from the hardware is what let us go from millions of parameters to billions, which is what ushered in this age of the foundation model.
That's a perfect transition. So once we have the tools and the hardware, we could finally build at this new scale. Let's make sure we have a clear definition of what a foundation model actually is.
At its core, it's really defined by how it's made and what it's for. It's a model that's been trained on incredibly broad general data, usually with self-supervision at a massive scale.
And its main purpose isn't to do one single thing well.
No. Its purpose is to be a powerful generic base that you can then adapt or fine-tune to a huge range of different tasks, whether that's summarization or translation or question answering.
And it's that sheer scale that's the differentiator. When you talk about something like GPT-3 having 175 billion parameters, what does that size actually enable?
It just completely upended the traditional AI workflow. Before FMs, you almost always had to start from scratch. Engineers spent most of their time on this laborious process kind of feature engineering.
Defining all the domain-specific logic to turn raw data, like pixels or text, into something meaningful the model could use.
Exactly. And every single application needed its own team focused on just that. But with a foundation model, that massive, incredibly expensive pre-training phase does all that heavy lifting for you.
It learns the powerful high-level representations on its own, just by processing enormous amounts of data.
Precisely. The model learns these rich statistical patterns, and the result is this indispensable shared substrate for entire fields. I mean, think about natural language processing after 2019. It's almost entirely built on top of the transformer architecture now.
And as you mentioned earlier, this is what unlocks those emergent capabilities. Can you give me another example of one of those?
A really clear one is complex reasoning. Smaller models can classify text, sure, but only a massive foundation model might suddenly be able to, say, translate between two languages it wasn't explicitly trained on, just because it learned general principles of language structure at scale.
Or generate coherent computer code from a simple English prompt.
That's a perfect example. That ability wasn't trained into it. It emerged from the sheer complexity and breadth of the data and the parameter count.
That sounds like a dream for developers. Maximum leverage.
But you've also pointed out that this homogenization, everyone relying on a few central models, comes with a massive liability.
It's a huge trade-off, you know. On one hand, you have high leverage. Yeah. Any improvement to the foundation model immediately benefits every single application built on it.
Yeah.
That's an efficiency miracle.
But the liability is the risk of a single point of failure.
It's enormous. If that foundation model has deep systemic flaws or biases, and it always does given the nature of its training data, those weaknesses just propagate everywhere. So if the base model has a racial bias, every resume screener or loan application tool built on it will inherit that bias.
And potentially even amplify it. It makes governance and auditing so much more complicated because you're not just checking 1,000 small models. You have to somehow vet one massive, opaque model that underpins everything.
That's a critical point. But before we get deeper into those risks, let's quickly trace the architectural evolution that even made these massive models possible.
Sure. The story really starts with some early successes. For vision, for anything with images, convolutional neural networks, or CNNs were foundational.
They were kind of inspired by the human visual cortex, right?
Loosely, yes. They use these layers of operations like convolution and pooling to recognize patterns locally, no matter where they are in an image. That's what gave them breakthrough performance on tasks like ImageNet.
Okay, so that was for vision. What about for sequences like text or speech?
For sequential data, where the order of things matters, we used a different family of models, recurrent neural networks, or RNNs, and especially their more sophisticated cousins, LSTMs, which stands for long short-term memory networks.
And LSTMs were a big deal because they could remember context over long sentences.
They could. They were introduced way back in 1997, and they were really ingenious. They used these internal gates to control the flow of information, which helped solve the vanishing gradient problem in sequence models. For years, they were the state of the art.
But they had a bottleneck.
A major one. They had to process data sequentially, one word at a time. That made training very slow and really hard to parallelize across lots of GPUs. It limited how big they could get.
And that's where the transformer architecture just swooped in and changed everything.
It's the critical piece of the puzzle. The transformer, which is the architecture behind models like BERT and GPT-3, it did something radical. It replaced that recurrence entirely with a mechanism called self-attention.
So instead of processing one word at a time, it could look at the whole sentence at once.
All at once. And that was the key to unlocking scalability. The attention mechanism lets the model weigh the importance of all the other words in a sentence when it's processing any single word.
And it can do it in parallel.
Which is perfect for GPUs. That ability to instantly see long-range connections in the data combined with parallel processing is what allowed for the unprecedented scaling that drove the whole foundation model revolution.
So we went from these specialized layers for specific data types, CNNs for images, LSTMs for text, to one dominant, super scalable architecture that works so well it can handle almost anything.
Exactly. And that scaling ability is what leads directly to this idea of universal knowledge extraction, or what we call representation learning.
Right. When you train a model at this scale, it's not just learning to slap a label on something.
No, it's learning a universal feature space.
Yeah.
Representation learning is this automatic process where the model extracts meaningful, abstract, and reusable patterns from raw data. It does it by processing these vast co-occurrence patterns across symbols, whether that's text or code or images.
So is the model actually understanding what these symbols mean?
That's the philosophical question. What it's doing is learning strong associations and relationships. It doesn't know what royalty is, but it sees that the word king relates to man in the same way queen relates to woman. It learns the latent structure of concepts.
And because it learns this from such diverse data, that knowledge is transferable.
Precisely. That abstract representation of tat that it learns becomes this powerful, reusable backbone. You can take that representation, which cost millions of dollars to create, and apply it to a new task, like classifying photos for your local animal shelter. And you'll need way less data and compute to get high performance. That's the power of transfer learning.
And a key method for this is self-supervised learning, like contrastive learning. How does that work?
Contrastive learning is basically about teaching the model to build a really well-organized conceptual map. The goal is simple. Push the representations of similar things closer together, and pull the representations of unrelated things far apart.
So if you give it two different sentences that mean the same thing, they become neighbors on the map.
Exactly. Those are positive pairs. But if you give it a sentence about astrophysics and another about ancient Greek history, those are negative pairs, and the model has to make sure they're mapped far away from each other. It forces the model to learn a really robust semantic understanding of the data.
And the practical applications of this are now showing up in fields you might not expect, like clinical neuroscience.
This is where it gets really incredible. Researchers are leveraging these huge pre-trained speech models, like one called Wave2Vec 2.0, and applying their knowledge to decode human thought.
Wait, you're talking about decoding speech directly from brain signals without invasive surgery.
That's right. They're working to decode speech from non-invasive MEG and EEG signals. The challenge is that this raw neural data is incredibly noisy and complex.
So how does the pre-trained model help?
They use the big speech model, which already has this rich understanding of language, to extract high-level semantic features. Then they train a much smaller decoding model to find patterns in the brain data that match those specific speech features from the foundation model.
So they're using the knowledge from the big language model as a guide to teach the smaller neural decoder what to look for.
Precisely. The power of that transfer means the system can then identify which spoken word best matches the decoded brain activity with surprisingly high accuracy. This is a huge step toward non-invasive communication for people with paralysis.
That's genuinely transformative. Taking knowledge learned from the internet and applying it to restore communication. It really shows how universal these representations can be.
It does, and it extends even further. Researchers have used public fMRI data brain scans to pre-train models to decode complex mental states, borrowing the same architectures that power GPT and BERT.
So they're treating the brain activity over time like a sentence.
Essentially, yes. And they found it significantly improved the accuracy of decoding mental states. The fact that the same principles work for text and for brain scans is it's a testament to the flexibility of these architectures.
Okay, so we've established these models are massive and powerful. But that size creates a huge practical problem. Fine-tuning 175 billion parameters is just not feasible for most people.
That's the critical constraint. Full fine-tuning needs enormous compute power, tons of specialized hardware. It's out of reach for most organizations. If we want these models to be truly accessible and customizable, we need a better way.
Which brings us to parameter-efficient fine-tuning, or PEFT. And the leading technique here seems to be low-rank adaptation, or LoRA.
LoRA is such a brilliant solution. It dramatically cuts down on the number of parameters you need to actually train. Let's go back to an analogy. Think of the big pre-trained model, the 175 billion parameters, as this huge, perfectly tuned engine.
Okay.
When you fine-tune it for a specific task, say summarizing legal documents, you're just looking for a small change, a small delta that adapts it.
But traditionally, you had to update the entire engine to make that small change.
Correct. LoRa's key insight is that this change you need is often low rank, which means the important adjustments live in a much, much smaller computational space. So LoRa restricts the update to two tiny matrices, let's call them A and B.
So instead of training billions of new weights, you're only training the small number of parameters inside these two little matrices. It's like downloading a tiny patch instead of the whole software package.
It's the ultimate engineering hack, isn't it? It's like adding these tiny specialized turbochargers onto the massive frozen engine. The product of those two small matrices approximates the full change you needed, but with a fraction of the cost.
And what are the results in the real world?
They're game-changing. You can reduce GPU memory usage by 75% or more. And it improves what we call sample efficiency. Because you're keeping all that general knowledge from the base model, you need much less task-specific data to get good results. LoRA is what lets developers quickly and cheaply customize these huge models.
That flexibility naturally pushes us beyond just text. The next frontier is multimodality, right? Integrating all sorts of different data.
That's exactly where things are headed. Multimodal foundation models are learning to integrate text, images, audio, sensor data, even code or biological sequences.
How do they do that?
They do it by finding the strong statistical links between massive paired data sets, so an image and its caption, or a piece of code and its documentation.
So the system learns this shared universal feature space where the word cat, an image of a cat, and the sound of a meow all end up close together on its internal map.
Exactly right. And that multimodal alignment is what powers the most visually stunning AI applications we see today. It's what lets models like DALL-E and Stable Diffusion generate these incredible high-resolution images just from the text prompt. It's translating a concept from the language space into the visual space.
And we're seeing it go beyond just generative art, back into scientific and clinical work.
We are. Diffusion models are now being used to reconstruct faces and complex visual scenes directly from fMRI brain recordings. The ability to turn abstract neural data into a recognizable visual image it's revolutionary.
And these models are proving valuable in fields like healthcare and law, which have traditionally struggled with data scarcity.
That's one of their biggest strengths. In healthcare, they can act as these incredibly sophisticated knowledge bases. We're seeing models like MedPLM that can process complex health records, summarize findings, and even help with drug discovery by generating novel molecules or experimental protocols.
Which could fundamentally change a field where development takes a decade and costs billions.
Absolutely. And then in the legal world, FMs can help automate legal research, draft documents, and this is crucial, analyze extremely long and dense texts.
Legal documents are famously long. I think a typical Supreme Court opinion is thousands of words.
Yeah.
That's been a real challenge for AI.
It's a huge challenge, but FMs with attention mechanisms are getting much better at handling these long contexts. That's vital for things like contract review or helping lawyers draft briefs. They can also adapt quickly to high-stakes, low-resource tasks like analyzing police reports to ensure race-blind charging decisions.
To enable all of this, though, we have to talk about the systems behind the scenes. The engineering required for large-scale distributed training.
This is the hidden infrastructure that makes trillion-parameter models even possible. You have to coordinate thousands of GPUs or TPUs to all work on the same model at the same time, and you do that with these complex techniques like data, pipeline, and tensor parallelism.
It sounds incredibly complicated. How do you coordinate all of that without communication just crippling the whole process?
It's a very fine balancing act. Data parallelism is the simplest. You copy the whole model onto every device and just give each one a different slice of the data. Pipeline parallelism is more like an assembly line. You split the model's layers across different devices. And tensor parallelism is the most complex, breaking up the individual large layers themselves across devices.
And the goal is always to minimize communication time and maximize compute time.
That's the whole game. And systems like Megatron and DeepSpeed are critical because they orchestrate all of this to get the maximum throughput. They're achieving incredible efficiency, but the resource requirements are growing so fast that it's a constant race between software and hardware innovation.
So it's about co-designing the hardware and software, right down to the number of bits you use to store the data.
Absolutely. Co-design is vital. A common trick is to do calculations in lower precision, like FP16, which doubles your memory and speeds things up, or exploiting weight sparsity, where you only compute on the non-zero parts of the model.
And once the model is finally trained, the challenge shifts from training cost to deployment cost to inference.
Inference is a huge factor. The cost and time to get a single answer from a trained model is what determines if a business case is even viable.
One of the more fascinating solutions here is the rise of retrieval-based models.
Yes, retrieval-augmented generation, or RG. The idea is brilliantly simple. Instead of trying to cram every fact into the model's parameters, which is expensive and hard to update.
You store the knowledge externally in a separate database.
Exactly. So when you ask a question, the system first retrieves the relevant documents from its library, and then it feeds that context to the language model to generate the final answer. It keeps the core model smaller, it's more efficient, and it's so much easier to maintain. You just update the text document, not the whole billion-parameter model.
That's a perfect example of optimizing for the real world. But now we have to shift to the significant ethical and societal risks that come with all this scale and homogenization. Let's start with the environmental cost.
The computational cost is immense, and we have to be transparent about it. Training a model like GPT-3 requires thousands of GPUs running for days or weeks, and that is incredibly energy intensive. The environmental impact isn't negligible.
So is the only answer smaller models? Or are there mitigation strategies?
Mitigation is key. While more efficient models are part of the answer, researchers have shown that the carbon impact can be drastically reduced by being smart about where you do the compute. Choosing energy grids that run on low-carbon sources, like hydroelectricity in Quebec, can make a huge difference.
That makes the energy grid itself an ethical part of AI development.
It absolutely does, and it leads us right into the critical issue of bias and inequity.
Because of that homogenization problem. A flaw in the foundation spreads everywhere.
That's the major liability. These models are passive absorbers of the internet, and they inherit and amplify all the intrinsic biases, representational, gender, racial, all that model that are in that data. And because one model is the foundation for so many things, those biases propagate widely.
Can you give a concrete example of that?
Sure. If their training data has limited information about, say, LGBTQ plus identity terms or sparse data on African Americans, the model just won't learn accurate representations for those groups. Then a downstream tool, maybe for hiring, uses that flawed foundation, and it will fail or perform poorly when it encounters data about those marginalized groups. It just reinforces existing inequities.
And beyond the data's inherent bias, what about intentional security risks?
Fundamentally, yes. The foundation model becomes a high-leverage single point of failure. It's a prime target for attacks like data poisoning.
How does that work?
An attacker might only need to subtly poison a tiny fraction of the training data. The goal is to make the model behave in a specific malicious way, but only when it sees a very specific trigger. For example, making a medical model misclassify scams, but only if a certain doctor's name is in the prompt.
And what about the misuse of its generative abilities?
That risk is intense. We call it dual use. These models can be used to generate high-quality, cheap, personalized, harmful content at scale, realistic deepfakes for harassment, or massive amounts of sophisticated targeted disinformation. The quality is so high it can overwhelm our ability to detect it.
And all of this is compounded by the fact that the models are basically black boxes, right?
It is. They're incredibly opaque. You can't just trace the logic. Their emergent properties are often unexpected, even to their creators. And that opacity creates an urgent need for interpretability and explainability, especially in high-stakes fields like healthcare or law, where you need to know the rationale behind a decision.
So if we step back and look at this whole landscape, what's the big takeaway? What is the transformation here?
I think the overarching shift is complete. AI development has moved from building these highly specialized, bespoke tools to adapting powerful, general-purpose intelligence engines. And that has radically democratized AI capabilities for organizations of all sizes.
Yet, as we wrap up, there's still this philosophical tension, isn't there, between the scale they've achieved and what they actually understand.
That's the essential closing thought. These models are trained on statistical co-occurrence. They're just predicting what word or pixel is likely to come next. And while their fluency is amazing, it raises the question, are they truly intelligent, or are they what some have called stochastic parrots?
Fluent mimics that lack any real, grounded understanding of the concepts they use.
Exactly. Their complex behavior comes from observing massive correlations in data, not from any internal model of causality or, metaphysics. And that's why the crucial consideration moving forward isn't just what they can do, but how we ensure they're aligned with human values and are reliable.
It forces us to think about the societal costs, and even ask the question of when we shouldn't build a model at all.
It has to. The focus has to shift back to human responsibility and accountability. That's where it must remain.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.